Hello and welcome to this session on using object-oriented programming in measurement systems. The goal today is to showcase why object-oriented programming is such an important design approach when developing large systems that need to scale. Now, admittedly, object-oriented programming may be a paradigm shift for programmers who aren't familiar with it, but hopefully today's session will make it more approachable by building upon concepts that should be familiar for the majority of LabVIEW programmers. So let's begin by examining the profile of different development flows and the relative investment over time. Now, many measurement systems, especially LabVIEW systems, begin as a relatively low investment, simple system with fairly finite requirements. But if over time new requirements and new measurement capabilities, new test capabilities, and new hardware support are going to be added to the system, these often end up becoming very brittle, very difficult to maintain, and a few years down the road, the investment necessary to maintain the system is extremely high, and people begin to talk about refactoring and redesigning code. So what we're going to talk about today, namely object-oriented programming, does require an upfront investment. It is a non-zero effort, especially if you're new to object-oriented programming. And so really, what we aim to do by making this investment is shift the effort to the start of a project, and by doing so, lower the effort over time necessary to support new features, support new measurements, add new hardware capabilities, etc. So again, by willingness to invest in the architecture and the training and the tools and the processes, you can hopefully drive down the cost of maintaining the system over time. Now, to be clear, object-oriented programming is just one of many different tools in your tool belt to help build such a scalable, highly maintainable system. There's lots of different answers to addressing that problem, but it definitely is a very well-adopted solution across most modern-day programming languages, and especially when developing application layer software. So fundamentally, you should be using object-oriented programming if you care about building highly extensible systems. And OOP does this by minimizing the scope of changes that have to be introduced in order to add new functionality. This is made possible because we have clearly defined interfaces, ownership of data, and association of methods that can act upon that data. And so we can derive from these to add new functionality to our system, as we'll see in a minute. We also protect the data encapsulated by a class or an object. And this way we're able to maintain an explicit relationship between data and the functions that are allowed to act upon it and modify it. OOP, as we'll see, also makes it possible to load new behaviors at runtime that implement those existing interfaces I just mentioned, but perhaps redefine how they are actually executed. And then finally, because we can derive behavior from parents perhaps that already have some data scope and even some implementations of functions, it makes it very possible to reuse these common methodologies and common pieces of data. So we don't have to rewrite code that's common across our system. We can just focus on extending it in specific and unique ways. So for all these reasons, OOP is a very compelling solution when needing a more extensible software architecture. So as I mentioned earlier, object-oriented programming is definitely a paradigm shift if you're not familiar with it. And I myself did not start out familiar with OOP when I started using LabVIEW. And when I finally came around to using it, I now realize that it's really not that far removed from what many LabVIEW programmers do already. So again, I kind of hope to chronicle my own learning path from the basic LabVIEW building blocks through to object-oriented design. And I will say that now that I really understand and value OOP, I tend to approach almost all software design problems with an eye towards the use of OOP. So at its most basic building block, let's use for the sake of example a LabVIEW system where we have to configure some hardware for the sake of acquiring some raw data and finally turning that raw data into a meaningful measurement. And we'll chronicle how over time, as we add new definitions of how we want to perform this operation, there are ways to better reuse this code and scale the complexity of our system. And in this theoretical system, you can imagine that within the confines of these particular functions or sub-VIs, we are defining the behaviors necessary to actually interact with the hardware, start some previously configured task, read the samples out of the buffer, stop it, etc. So hopefully we're at least at a point in our LabVIEW expertise where we're making effective use of sub-VIs, connector panes, passing data, etc. So of course these sub-VIs are going to require some form of data in order to do their job. So we can see here that the configuration needs to know which task and which clock to use. We'll need to know the number of samples for the acquisition, of course the DAC task that we previously configured. The sample value will have to be shared with the measurement task, perhaps for the sake of windowing on an FFT or something. But as we can see, basically these sub-VIs have well-defined sets of things they need to do their jobs and the data they will return once they've completed their task. So eventually we may want to repeat a part of the program, so we put one VI in a loop. Or perhaps we want to rerun the entire task on a repeated basis. Or we actually want the ability to control the order in which these operations occur or are repeated. And so you likely eventually arrive at the basic LabVIEW state machine architecture shown here. We have our case structure, we have a case corresponding to each command, and the data that we have to pass between the functions is now passed via shift registers. Now, one concept that I really want to emphasize is data scope, and I'll probably talk a lot about this in this session. But data scope is defined as the scope of information that a given loop or set of operations have access to. And so in this case, looking at this particular state machine, the scope of data corresponding to the state machine is really illustrated by the shift registers that are being passed between the different states of our state machine. Because again, all of the VIs and operations contained within the different cases can operate upon the scope of data defined by these shift registers. Now, one point we'll come back to is that we want to be really conscientious about the data scope that we associate with a given task or operation. We want those to be very logical, cohesive groupings of data. We don't want to overextend the scope of data such that we have way too large of a cluster or way too much information contained within a single loop for a number of reasons, most of which really limit the scalability, extensibility, and the readability of source code. And so finally, we have our state machine. Its data scope is defined as all the parameters we saw earlier being passed into these various functions. Great. So being a savvy LabVIEW programmer, we realize that over time, this scope of data and the number of shift registers may continue to grow. And so the logical course of action is to go ahead and just group all of that into a single cluster, make it a type definition, and that way as we have to add new parameters, we're not going back and modifying every single connector pane. We have a strict type definition, so everything just updates. And if we look through the different cases in our event structure, we can see that we're unbundling the data these operations need and bundling the data back in. Again, in an effort to increase the scalability of our code, we go ahead and just pass the type definition directly in. That way, if we ever have additional parameters we want to pass in, well, it's in the type def, so we can go ahead and just unbundle those inside the context of the sub-VI. So in a way, this is our first step towards a more scalable architecture, but there's some problems with this that we'll talk about here in a minute. So if we flatten out the contents of that state machine we just looked at, we fundamentally have this collection of data, again, our data scope, and the methods that are allowed to act upon that data. So without even realizing it, you've basically created a direct relationship between these VIs and this cluster. So you could say they're explicitly coupled to this cluster of data. Well, conceptually, a class is essentially identical to a cluster. And so if you're completely new to object-oriented programming, that's probably the first most important concept you really need to understand. In fact, when you first create a class, as we'll see here in a minute, the first thing that you do is define the cluster of data contained by that class. So a class contains a data cluster. It also defines the set of VIs that are allowed access to that data cluster. VIs that do not belong to that class cannot access that data. And so that's one of the first biggest and most important distinctions that separates a class apart from a cluster. With a cluster, anyone who has the cluster wire can access and modify the data. Again, with a class, only VIs that belong to it have the rights to do so. So returning to our example that we've been using, instead of passing that cluster between these three methods, now we're just passing the object wire. And that object has a private data cluster inside of it that has the same data scope as the cluster we saw earlier. But in this case now, we've protected access to that data. Only these VIs, assuming they belong to the measurement class, have the ability to read from or write to the private data control contained within that class. So stepping out of abstract examples, we see the appearance shown in the LabVIEW project on the right side of the slide. So when you create a new class, you'll actually get a new file on disk, which is an LV class file. You'll see a private data control inside of it. And this is where you define the scope of data that the methods inside this class have access to. And then as I mentioned earlier, the thing that sets a class apart from a cluster is that we actually have a set of VIs or methods that belong to that class, and only they have access to the cluster. So we denote that literally by adding VIs inside the class, and you can see in this tree view here that they're actually shown in the project beneath the class itself, indicating that they are owned by the class.
All right, so let's quickly go through the basic mechanics of actually creating a class in LabVIEW. From the Project Explorer, you'll right-click on either your target or a folder you want to store a class in. You could also right-click on a library, and we'll select New Class. And in our example, we'll just type Measurements, which will be our base level class. And if we hit Save All, that will prompt us to store this class, which is the LV class extension, somewhere on disk. And as a general best practice, I always put classes inside of new folders and put their methods in there as well. So having saved that, let's take a quick look at what we now have in the project. We have the LV class item, which serves as a container. Inside of it, by default, we will always have a control, and this is where we store the private data or define the data scope of our class. And let's right-click and see we have the full palette set, and let's do a basic numeric control for number of samples. All right, and then finally, it's important to realize that if we go back to our class and right-click on it, there is a different menu of options under the new menu. And here we can see how we create various VIs or items belonging to that class. We could also drag VIs in, at which point they are then considered a member of this class. And we'll come back to this once we've looked at what terms like dynamic dispatch mean and when and why you should use them.
So now that we've created our first class and defined the data scope of it, we can return to our block diagram, and where we previously had the data cluster being passed through the various member VIs, we can now actually replace with a class. And so again, that class is conceptually the same as a cluster, and this graphic is just really aimed to illustrate that. So the functionality of the code we're looking at here is identical. We have the private data control being stored in that shift register, passed inside the state machine, and these VIs are acting upon it just like they would if it were a cluster. The only difference is that, again, because it is a class, there is protection of the data such that only member VIs can access it. All right, so having arrived at this point, we hopefully understand that a class is conceptually the same as a cluster. But as our first illustration of how a class improves the scalability of our code, consider, for example, what you would do if you want to be able to reuse this code and calling architecture, but be able to define a different set of behaviors. So for example, a different measurement, which would have to do different things in order to configure a hardware task, acquire from it, and actually measure from it. So one of the first and very important distinctions that separates a class from a normal data cluster is the ability to inherit from a parent class. So what that really means is that in this case we have a measurement class which has its own defined data scope and its own defined set of methods that can act upon that data scope. A class that derives from it or inherits from it actually inherits its data scope and its definition of methods that can act upon that data scope. So for example, we have a strain measurement or a diode characterization measurement. These are able to reuse methods and data belonging to the parent, but they're able to extend and customize and even add new functionality that is specific and unique to that particular measurement definition. These two classes are considered children of the measurement class, and we refer to strain and the diode measurement as siblings of one another.
So let's go through the process of creating a child class of measurement. Again, we'll right-click on my computer, create a new class. In this case, we'll call it temp. And once again, we'll quickly go through the process of saving this to a separate folder. And at this point, this is not a child of measurement. To change its inheritance, we right-click on it and go to Properties. And from the Properties dialog, you'll select Inheritance. Notice there's a lot of other menu items here, including the icon of the class and class members, etc. But skipping ahead, we'll go to Inheritance. And here we can see that it inherits from the basic LabVIEW object, and that is the basic class from which everything is derived. But we want to change the inheritance and have it be a child of measurement. We'll go ahead and inherit from selected. We'll hit OK. We'll save these changes. And just to illustrate the impact of doing this, we can right-click and say Go to Parent Class. It'll show us the parent. We can also right-click and say Show Class Hierarchy, at which point it shows us that temp is a child of measurement. Well, returning to the diagram we saw earlier, we see that changing the behavior of the system is as simple as passing a new object down this wire. In this case, if we pass a temperature measurement, this object has a unique data space and defines the way in which these operations should execute. This is made possible thanks to a technology known as dynamic dispatch. Dynamic dispatch is similar to polymorphism, but unlike polymorphism, the function selection occurs at runtime instead of edit time, and this is based on the object that is passed into the dynamically dispatched VI, specifically the dynamically dispatched connector pane. In this case, if we pass a temperature measurement into this block diagram, the object has a unique data space and defines the way in which these operations should execute. This is made possible thanks to the fact that the method shown here, acquire, is actually a dynamically dispatched method. Now, dynamic dispatch is similar to polymorphism, but unlike polymorphism, the function selection occurs at runtime instead of edit time, and this is based on the object that is passed into the dynamically dispatched terminal of the VI's connector pane. So assuming the acquire method is dynamically dispatched and that both strain and the temp classes or objects override it with specific implementations, we can see that this particular method belonging to the strain class will actually behave differently depending upon the object we pass into it. So whereas previously we had a single finite acquisition, perhaps in this example we have a stimulus response acquisition defined. All right, so now let's take a quick look at how we create and use dynamically dispatched VIs belonging to a class. We'll go back to our parent measurement class, right-click and say New. And here we have all the different types of VIs and things that we can add to the class. We'll go ahead and select VI from Dynamic Dispatch Template, at which point it generates a new class on disk. I'm going to hit Control S to save it. Note by default it's going to put it in the same folder as the class that it contains, or that contains it. So we'll call it Acquire. And also I want to draw your attention to the connector pane, as a VI belonging to a class has an additional option for what type of connection an item on the connector pane should be. And so here it specifies that this particular input terminal is a dynamically dispatched input. Similarly, the output terminal is as well. Okay, so having created this new acquire method, let's now save everything, go to the child, and if we go to the new menu, we'll notice that we have a new option called VI for override. And this will actually give us a dialog displaying all of the methods belonging to the parent that the child can re-implement. So we'll go ahead and hit OK. This will generate a new method belonging to the temperature class. It has the exact same connector pane as its parent. As promised, when we hit save, this new VI is by default placed in the folder alongside its parent. A few other niceties that are worth pointing out while we're here includes, for example, that with OOP you can actually enforce some rules for other programmers. One of which is that we can actually demand that all children of a class implement a specific dynamically dispatched method. So that can be a way of enforcing rules for other programmers and making sure they abide by set interfaces. We can also require that a definition of a dynamically dispatched method in a child has to also call the parent's copy of it somewhere on the block diagram. Again, another example of one of the rules that helps enforce uniformity in programming practices as well as code reuse. So to illustrate the experience of using a class hierarchy and specifically dynamic dispatch from a block diagram, we have a slightly more sophisticated example here. It's basically building upon the concepts we've seen earlier, where we still have a base measurement class. And if we go take a look at the class hierarchy, the window will show that we have 4 children derived from the measurement class, specifically diode characterization, frequency measurement, resistance, and strain. Now, as we've seen in our examples and slides, the parent measurement implements configure, acquire, and measure interface. Now, keep in mind it also includes a lot of other VIs as well, but these are the ones that are going to be overridden by children. And at edit time, if we actually wire up one of the children, we'll see that the compiler will actually tell us that in this case, the diode child class has overridden acquire, measure, and close, but has not overridden the method to configure the particular measurement. And so you can tell that just by looking at the sub-VIs. So likewise, if we wire in strain, we can see it overrode configure and acquire, but not measure and close, so on and so forth. Frequency overrode acquire and measure. And of course, if we wire back in our parent class, it uses the same interface. Now, because these are all members of the same class hierarchy too, we can also actually build these into an array, and we'll just quickly do that for a few of these. And the array can consist of the leaf level classes as well as the parent. And so again, even though these encapsulate different data scopes, we can actually pass those along the same wire. And of course, we'll need to drop a loop of some sort around our code. And here we can see that that is actually valid syntax. And basically, because we have an array of 4 elements, this for loop will iterate 4 times. Each of those 4 times will execute a different implementation of the methods that have been overridden by child classes. All right, so now that you hopefully understand the power and use of dynamic dispatch, we want to take a few minutes to dispel some common misconceptions. For starters, many people when learning dynamic dispatch and object-oriented programming ask the question, well, isn't this just the same as using a case structure? And to clarify this question and to examine the differences between the two scenarios, here we see 2 supposedly functionally equivalent programs. On the top, we have our object-oriented approach, where we have a class that defines the data scope and the implementation of the interface for configure, acquire, and measure. And then down below, instead of having a class encompass the data scope and define the cluster, we can see the cluster being passed, perhaps as a strictly type definition, into the configure, acquire, and measure methods. Now, because we want to, at runtime, select what type of measurement, we have used perhaps an enumerated constant that's driving the input terminal of the case structure. Well, this begs the question, what's the difference? And I think as you'll see, there are some very key and important differences, especially with regards to scalability. So, to better understand these differences, let's take a look at what needs to be changed to the functional block diagram if we want to add the definition for a new measurement. Well, the first thing we would need to do is modify the enumerated constant to represent the new measurement type. And mind you, this may be a string, whatever, it doesn't matter. The point is that right off the bat, we are automatically going to be touching and changing a lot of code, namely all 3 of these sub-VIs. And as we'll see, one thing that needs to go hand in hand with designing a scalable system is designing it such that you are isolating the impact of changes. If you know and accept that changes will be introduced to your system on a regular basis, you want to do everything you can to make sure that those areas that are subject to the most amount of change are somewhat isolated, and you're minimizing the ripple effect throughout the rest of your code, because the propagation of changes introduces risk and requires revalidation. Anyway, so right off the bat, we've changed a lot of code. Second up, we actually have to go into these sub-VIs and modify all of them to implement the new methodology. So we have to do this at edit time. Certainly doable, but over time, if you end up with a large list of measurements, we end up with a lot of code defining the behavior of a lot of totally different things in the same block diagram. And then finally, I think one of the telltale signs of code that is not going to be highly extensible is when your data cluster begins to grow in scope and begins to encompass fields that pertain to one of a handful of measurements, and then there's a lot of other fields that don't pertain to that specific measurement but rather to others. And over time this becomes difficult to debug and know who's setting what parameter and even who's using which parameter. These are three major ways in which we will likely impact this system. And as we'll see, if we were to do this with object-oriented programming, a lot of these challenges would be much better addressed. So the last point about the scope of the data growing over time is really worth emphasizing. And this is a common code smell, which is a colloquialism many programmers use to refer to a clear sign that something's just not written well. And so in this case, we see our clusters already beginning to get bigger. And this goes back to the original point about data scope. If the scope of that data is not a logical grouping, consider that you have the thermocouple type next to the strain bridge type, two things that you would likely never be using in the same execution path. No measurement would ever likely need to use both of these. Then we might need to look for ways or alternatives that would improve the scalability of the code. Large data clusters ultimately stand to become very brittle and difficult to debug and maintain. So alternatively, going back to our class-based implementation, we see next to these objects a hypothetical data scope belonging to each. And your base level class, in this case the measurement, should define a data scope that is universal and used by all children of this particular class. And so here we can see that in this example, our requirements are such that every single measurement would need to define the number of samples it needs to take, would need to have an I/O parameter, and a task constant. But if we look at the strain measurement, it's going to inherit this data scope, plus it's going to add to it the type of bridge to use and the source of excitation, whereas the temperature measurement would just add a field for thermocouple type. And so one way to look at this is that the data scope of strain becomes its parameters plus those of its parents. But of course, it can't access the data scope of siblings. So right away, we are ensuring that an atomic operation, or the definition of a class, has a logical and cohesive data scope that is decoupled from similar but different definitions of, in this case, a measurement. Another very big difference between OOP and functional programming is how flexible a calling framework can be. So if we want to be able to add a new measurement to the functional code shown here, we need to do so at edit time. But with classes, we can actually add a new object at runtime. We can even load a new object into memory after execution has begun. So at edit time, we'll see LabVIEW indicate the instance of the object that it thinks is going to be run. If you simply replace the object wired into this interface, the wire will now show the specific type of class, and the methods will display the icon of the appropriate method. So if we wire in the temp measurement, we'll see its methods and its wire, and likewise for strain and likewise for measurement. However, if you want a plugin architecture, we can actually leverage this concept to, at runtime, pass an arbitrary child of a common class along this wire. And as long as the interface is common to this particular object at runtime, that object can then define its own implementation of these interfaces, or if it doesn't, it can opt to use the interface of the parent. And so to be clear, this class we run at runtime can have a unique data scope and can define new implementations of these dynamically dispatched VIs. None of this needs to be known by the calling framework ahead of time or before compilation. So we can actually do this from an executable. And this is a fairly standard pattern that is typically known as a factory pattern. It's actually a very simple pattern. In fact, we're showing the core of the code to implement a factory pattern. the get LabVIEW class default value is pointed at a location on disk and loads new object into memory. Now, you do at edit time need to tell the compiler what type of object to expect in order to utilize the interface for that particular object. You do this using the toMore_specific node. So using this node, you'll wire in the parent class for the plugin or the parent of the plugin that defines the interface. And if at runtime this is a valid child, the child class will be passed out. Of course, if not, an error will be returned. Okay, so at this point, taking a minute to reflect on what we've learned so far. We've talked about encapsulation, we've talked about inheritance, dynamic dispatch, and these are really the fundamental and most important concepts you need to really understand in order to use object-oriented programming effectively. So now that we have these, let's try a simple exercise. So if we continue with our previous example and imagine that we have the two measurements we've discussed before, strain and temp, assume that we've now overridden the dynamically dispatched methods for configure, acquire, and measure. One of the first stumbling blocks people often encounter is that they either need to supply or receive a unique value to or from this measurement. To keep it simple, let's consider how you return the measured value from the object, especially if temperature and strain measurements will return different values. For example, a waveform versus a Boolean, or even an integer value. So, given what you know now, how might you go about designing the system? And keep in mind that dynamically dispatched methods have to have identical connector panes. So we show the big red X on the bottom example because it cannot pass a different data type out of its connector pane. It has to match the parent's implementation exactly. So what do? Well, let's further consider some options. We know a measurement will always run or return a specific type of result. And according to this, requirements include that a result may need to be displayed in a manner that is specific to the data. So think about the fact that there's a relationship between the data and methods that act upon that data or display it. This type of approach is common when building a framework that needs to call a standard interface that is capable of displaying and doing different things. Now, a variant is not the answer we're looking for, though it can be used, and it's what many LabVIEW programmers often gravitate towards in a situation like this. It can work. The challenge is it risks creating code that is not easily scaled, and of course, that's exactly what we're here to do. And this is because we have to add logic to ensure the data is cast to the appropriate type at runtime. And we might need to drive behaviors like display data based on that data type, but this becomes difficult to extend over time. So in this scenario, consider the use of a class hierarchy that represents the result of a measurement. So perhaps we have a base definition of a result and the interface that it implements, like display, save, load, log to database, etc. And then each measurement, such as strain and temperature, carry with it a definition of a child of that result class that defines what data should constitute a result and how that data might be displayed to an end user. And frankly, once you start doing object-oriented programming, it's a slippery slope, and I mean that in a very good way. As we see here, the use of OOP kind of lends itself to using OOP for other aspects of your system. And we could extend that further if you begin to evaluate how you pass configuration parameters to the different measurements, and perhaps how to know how to read different configuration files and what parameters to look for or parse, and then how to store those in the private data. All of that might be an opportunity to use another class hierarchy. Anyway, to kind of summarize this section, one general best practice is that you want to avoid the use of variants. These are typically used when different data types have to travel down the same wire. And anytime you feel the need to do this, especially in a very large scale, consider replacing that wire with a class hierarchy. And one of the biggest benefits is that classes will still enforce that strict data type that LabVIEW programmers are so used to, and it will enforce it at edit time, thereby ensuring that you won't have to wait until runtime to see erroneous behavior. And variants do not allow us to capture mismatched data types at edit time, and so therefore increase the likelihood of runtime errors. So for the last section of this presentation, we want to take a look at how we can apply what we know about object-oriented programming and this very abstract measurement definition to consider how we might interact with real hardware. And so this, as promised, gets to the topic of a hardware abstraction layer. Now, before we get to the solution, though, consider the problem statement we're trying to address. We want to be able to run the same measurement on different machines, which may have different hardware or different configurations of hardware. We may want to continue development on a machine with no access to hardware, which you can imagine means we want to be able to run the system, perhaps with simulated data parameters, but we want to have the system in as close a state to the real finished deployed state as possible. And this is especially true of extensible, scalable systems. We often anticipate the need to add and change hardware over a long period of time. But of course, we don't necessarily know what future hardware will need to be able to do, or its capabilities, or even have access to its driver. So we want to be able to add a new device of a certain type without modifying the measurement that is expected to interact with that particular device. So in this case, we have our temperature measurement, which, for the sake of example, needs a DMM. In order to acquire, we need to implement the method using the generic interface for a DMM, but we won't know until later which DMM we want to use. And so here we blow out the contents of this sub-VI and consider, for example, the interface of the DMM to be configure, auto zero, read, etc. So once again, we have a very simple class hierarchy. The base DMM class implements the interface for how we expect a measurement to interact with a DMM. And then we override that with children that use that interface to call the specific device driver and basically wrap it with a thin layer of abstraction so that we can include it into our system without modifying the calling code. So before we go too far, let's consider in this particular example that we have a wide array of different hardware devices, all of which have different interfaces. So in our previous example, we used a DMM, but you might want a measurement that uses a scope or a frequency generator or a power supply, or uses multiple combinations of those devices. Again, each of which have different interfaces. If we're going to pass those into the measurement, how do we do that? Well, all measurements, in theory, use an array of hardware. It might be one device or an array of devices. But in order to pass this array of devices down a common wire, they need to all have a common parent. Because remember, if you're building an array of classes, that wire will be of type belonging to the common class that is a parent of everything along that wire. And so in this case, that wire we're seeing between the array and the configure method will almost certainly have to be a generic hardware class. And so in this example, this is the proposed definition of one particular hardware abstraction layer. So you have a base class called hardware that does not implement an interface other than very rudimentary interfaces necessary for the framework to call and use hardware. For example, maybe there's a method to return what type of hardware it is. But it's really the layer in the middle, shown as power supply, DMM, scope, and generator, that will define the interfaces for specific devices. So each of these will have appropriate methods, and then the children of that middle layer will again be the layer that wraps the actual driver calls to provide that thin layer of abstraction. Now, in order to make this work, we need to be able to, at edit time, tell the measurement class which interface we should be expecting to use. And so while we pass in an array of hardware objects, and perhaps we store that in the private data control of the measurement class, if we look at how those are actually used inside the code, we'll have to have a contract between the measurement and the framework guaranteeing that we know to expect certain devices in certain orders. So perhaps the measurement class tells the framework, I want a DMM and I want a scope. And so, assuming the framework abides by this contract, we can then cast the generic hardware classes that are received by this method to the concrete definition of the interfaces for DMM and scope. And then furthermore, at runtime, the leaf level definition of these classes will be passed in and will actually interact with the device drivers to do the measurement and return the values we need. Of course, if an incorrect device is passed into this method, it will return an error. Because these sub-VIs are actually being dynamically dispatched, double-clicking on them doesn't just open an arbitrary implementation. It's actually going to prompt us with this dialog for which particular instance of this method we want to see and explore. So again, another example of some of the subtle differences when using dynamically dispatched sub-VIs. So for our final example, we're actually going to open this sub-VI here, and this is going to launch a framework that exemplifies a lot of the concepts we've talked about in today's presentation, including the ability to dynamically load, call, and run definitions of both measurements and hardware. So here we can see this UI is presenting us with some basic information, including the fact that it's loaded the 4 measurement definitions we saw earlier. Each of these define a specific type of device that they need. For example, this might need stimulus from a power supply and to read a signal from a DMM. But it's at runtime via this user interface in this example that we will pass the concrete implementations of the device that should be used to actually run the particular measurement. And more importantly, because this is built using a factory pattern, this actually allows us to create a new child of the measurement class or the hardware class and load those into the system at runtime and call them. And this code is available for download if you want to experiment with this and see how it works for yourself. You can find it at bit.ly/lv_OOMAL. So LabVIEW _object-oriented measurement abstraction layer. So let's take a minute to summarize everything we've seen here today. We always want to be thinking about data scope. Keep it cohesive and keep it small. If you're not using OOP yet, look for loops and look at their shift registers and look at the size and scope of your clusters. If they're getting too big, it may be a prime opportunity to evaluate the use of classes. Keep in mind, we've learned that classes actually create and define data scope and a set of functions that are allowed to access that data. Also keep in mind that a child, it will inherit the data scope of its parent. It's worth noting, I didn't point this out earlier, but a child class does not automatically get access to its parent's private data members. It only gets access to private data members that are exposed via accessors. Now, again, if you do have a massive data structure, that's indicative of an overgrown data scope, so consider using that as a prime opportunity to instead leverage a class hierarchy. Dynamic dispatch is perhaps one of the most important fundamental concepts you really need to understand to do effective object-oriented programming. So make sure you have solidified the definition of dynamic dispatch, but at its most basic level, it is a type of method belonging to a class that can be overridden and redefined by a child of that class. It doesn't have to be, and if it's not, when called, the parent's copy of the method will be used. Again, many people mistake it for polymorphism. The key difference, though, is that it is basically occurring at runtime instead of at edit time. Also, it's the parent that should be defining the interfaces, and children should actually implement those interfaces, just like we saw with the hardware abstraction layer, where the children are the ones actually calling the device drivers. Also, if you find yourself using a lot of variants, here again, consider using a class hierarchy. And finally, the whole point of the session was to showcase that OOP is not quite the leap that many LabVIEW programmers mistakenly believe it to be. So if you think it might be too big of a paradigm shift, or you're worried about spending the time and effort necessary to get up to speed, it really should be driven by whether or not the problem domains we've talked about here are reminiscent of what you're struggling with and trying to get your arms around. And if it is, we maintain it's really worth the investment of learning how to use object-oriented programming effectively. Now, beyond today's session, we do have an entire customer education course dedicated to object-oriented programming. You can actually self-pace this online or sign up for an instructor-led course. Visit ni.com/training/self-paced to learn more. If you really want to dive deep into some of these concepts beyond the customer education course and the online course, consider getting your CLA or CLD. The summits, which are conducted by and organized by users, proved to be one of the most impactful forms for really learning how to apply some of these advanced design practices to the systems you're building. It's a great networking opportunity and fosters the exchange and sharing of ideas across industries and application areas. So if you're interested, visit ni.com/CLA-summit to learn more about this and other opportunities to get involved with the CLA community.